In this video we're going to take a look at some of the reversing challenges for the HackTheBox and Synack RedTeamFive CTF, which is running at the moment. As with the web video, we're going to start off with the easiest challenge first. Well, not in the order of the challenges, but in the order of the number of solves. So the check challenge says, can you help us reveal the secret? And there's no server to connect to, we've just got a downloadable file which I've already got downloaded. So we can go and take a look at it and see that it's a 64-bit executable. Don't really need to worry about the LSB or the Pi bit for a reversing challenge. It's not stripped, so we can read the function names and makes it a little bit easier to reverse engineer. So first thing we want to do is make it executable, and we can try to run it. It asks us to enter in a secret, so just try and enter something in here, see what we get, and we get incorrect. So we could open this up in Ghidra or in GDB or something to have a look to see what's going on. How I actually solved this at the time was just to run Ltrace and just try and enter something in here, and we can see that there's actually a string compare being done with the value that we enter. So we just take a copy of that, run it again and enter in that string, and we'll get back this flag, HackTheBox, check and recheck again. But let's see how else we could have done it. We could have opened GDB-PwnDbg, open up check. We can have a look here at the functions. We've got our main functions, so let's disassemble. Let's disassemble main. And in here we can see where's the string compare. There's a string compare being done right here. So we could set up a breakpoint here. Because Pi is enabled, we can't just specify the address yet, so we first need to run the program. Let me do break main and then run, and then we can say we want to, well, we could just grab the address now. Let me just let's disassemble main again. Now we can see these addresses are populated because the program's running. And sorry, let me minimize this in the background. So now we can see that the string compare is at this address, so we could just take a copy of that. And let's say we want to break there. Let's continue, enter in a secret, 1, 2, 3. We hit this breakpoint, and you can see then that the check is being done. It's comparing what we've entered, 1, 2, 3, against this check and recheck again. So that's another way we could have worked that out. We could also open it up in Ghidra. Let me close this down. So here we can go to our functions on the left and go to our main function, where we have our disassembled code here on the left and our decompiled code on the right. And we could basically go through, so this is going to be the characters on the getting placed on the stack, which are the same as the password that we just entered. So you can go and highlight them on the left here and see that's an A, that is a G, that is an A, so this one is AGA 1 N, so that's again, so we know that the flag was check and recheck again. So you can go and do it that way. I guess it's a little bit easier to do with Ltrace or with GDB because you can just copy and paste the flag, whereas here it's kind of all set up separately. But there's a few different ways we can solve the first challenge. The next challenge is called Access, and the description says, please help us access this classified program. So we've got the file downloaded again, and I've already got it opened up in Ghidra, but let's just go and make it executable first of all, and try and run it. You can see this time we've actually got a bit of animation, which can actually kind of make it quite hard to work with. For example, if I go, let's just try and enter something here first of all, 1, 2, 3. Access denied. So in our previous challenge we used Ltrace, but if we use Ltrace here, this kind of makes it quite hard to trace what's actually going on. I think again, let me try and enter in a value. Yeah, so it's not just, we can see the string length there is being checked as 14. Let's try and run that again. It's quite slow because we have to wait for the animation though. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4. We enter that in, and the string length, okay, it's still doing the string length check, but we get access denied anyway. So it's going to be a little bit harder to debug that way, and the same with GDB. Let's jump over to Ghidra and see what's going on in there. So we can go and have a look at the functions again. We've got a main function, and if we go and have a look at the code, we can see it's asking for this agent ID. The string compare is being done right here with 31337. So that's what we need to enter in, and then it's going to ask us for a pin. But let's try and run it first of all. I wish this was a little bit quicker. We enter that in, now it asks us for a pin, and you can see here if ivor1, okay, so it's actually got a check pin function. I'm just going to enter something in here anyway. Access denied. Let's go and have a look at the check pin function. And if we have a look in here, we see that it's the first thing it's going to do is get the string length, and it's going to loop through, so it's seeing how many characters are there, and then for each character it's going to XOR it with 0x20, so hex 20, which is 32. And what's the XORing? Well, it's XORing, you see this local 24, that's the loop counter. So you have this part of the .data section here, and you can kind of see some characters here like let me in, but there's some other stuff in there as well. And it's basically looping through each one of these characters, and it's XORing it with 20 in hex or 32 in decimal. So what we could do here, I actually, for me, I think the easiest thing to do here was go over to Redair. So you can run R2, R2 provided the file. You can do AA to analyze, and then AFL will show the functions here. So you could say smain and then PDF if you wanted to disassemble this and go and start having a look through the code. In our case, what we're interested in here is the sections. So if we do IS, it'll show us the different sections of the program. We've got the .data section here, which we know is where the where that value is being grabbed from, which is going to be XORed. So you can see where that is, but we can also see that here. So it begins at 2014. So let's do px 0x000. What was it? 2014. And it's asking, do you want to print all the lines here? Let's just say yes. We can scroll up through some of this to where the data is, and you can see the data in here, this let me in. So what I did here was just grab this, and you could take it to, you could unhex it in Python or in your terminal or something if you have PwnTools installed, but I'm going to take it to CyberChef because it's quite easy for us to do the XOR then as well, although it's quite easy to do that in PwnTools as well. So let's say from hex. Okay, it never seems to drag over for me anymore. From hex. Okay, so this start bit is part of that weird printing part. So let me go back there. Remember we were starting at 2014, wasn't it? Let's go back here. 2014. At the moment we've grabbed everything from here. You can see this part as well. So actually we wanted to start from about here. Let me take out the first couple of bytes. I think that's looking better. And we want to keep going on the next line as well. Grab those, paste those in, and I don't think it's going to go all the way to the G, is it? No, that's the global secure connection bit. Alright, so that's a new line there, the 0A. So I'm going to presume the new line is not part of it. Everything up to the new line probably. So let's try it. Let's say XOR, and we're XORing with a hexadecimal of 20 or decimal 32. And there we go. We do that and we see that we get this output. Let me get rid of that space at the start. Okay, that's looking good. Get rid of the space at the end as well. Okay. So that should be everything. If we go back and try to run this, let's exit Redair, run access, and first we need to enter 31337, and then next we can just paste in this pin. We get access granted, submit the pin in flag form. So the flag is going to be HackTheBox. The next challenge is called split, and the description says take control of the spy mobile and guide us to the flag. So I've already got the file downloaded. Let's go and take a look at it, make it executable first of all, and let's just try and run it, see what happens. Okay, it's got another one of these kind of slow interfaces, but it asks us for a destination node. Let's just try and enter something in, and we get incorrect destination, taking a U-turn. Alright, let's jump over to Ghidra, and in our functions here we've got a main function. If we decompile this, quite a bit more going on in this case. It looks like we have some kind of key which is set up here. We have some data in the .data section as well, so maybe something that's going to be decrypted. You can see it asks us to enter this destination node in, and it's going to read it into local 78. So we could hit L here and say dest node, just so we know if that's used again and where it's used. You can actually see it's used down here, and this looks like a key. I'm going to rename that as key just in case it is. This looked to me like it was some, well, we know it's from the data section. Let's say data. I'm presuming it's the encrypted data. You'll know because it's filled in the data down here as well now. Local 80 is the size of the data. You can see here string length data, and then this is calling malloc. So let's say data size. And you can see this is starting to kind of come together now. But we don't necessarily need all that. The way I looked at this was we have ptrace here, which what that's basically going to do is if we try to run Ltrace, or if we try to run GDB, it's going to cause some problems. Although it didn't actually. Oh, anomaly detected there. Yeah, okay. So anomaly detected if we have ptrace enabled. But what we can do is we can actually use PwnTools to patch the binary. So I'm going to create a new file called patch.py, and this is pretty handy. You can just say from pwn import all. Oh, why is it so small? And then we'll say, we'll load our binary. We'll say exe is equal to split. We'll say that elf is equal to context.binary, which is also equal to elf exe. You can turn checksec off. Some of this isn't really important, just a habit of doing it. And then we can say elf.asm, elf.symbols.ptrace, and then we're going to replace any. Basically, this is a function which is inside the binary. If you wanted to print this out, you could print out like here, pretty print elf.symbols.ptrace, and get an idea what. In fact, we'll do that as well just to get an idea. But essentially, we're going to basically replace this function with a return instruction, just so that function won't be called at all. So then we just do elf.save, and we're going to save it to patched. And hopefully that'll be it. Let's try and run it. We run that. Okay, we need to update PwnTools, but that's fine. Oh, it didn't print out. Oh, sorry. Elf.symbols we want to print out there. Let me just run that again. Run that again, and that'll give us all the symbols and the addresses. In our case, pi is enabled, so it's not giving us full addresses, it's just giving us offsets. But yeah, if there's any other functions we wanted to get rid of, really, we could do that as well. So now if we try and run Ltrace, oops, we need to chmod plus x patched, and then we'll run patched. Oh, sorry, Ltrace patched. Now if we run it and try and enter in a value, we get incorrect destination, but we don't get that anomaly detected. So we've successfully patched that out of the binary. So let's go back over to Ghidra, and let's look at the next condition. So we also have here, this is what we're running into, incorrect destination taking a U-turn, and it's checking if local 94 equals 1. So we need local 94 to not equal 1 if we want to get down to this decrypt function. So local 94 is set here. We could rename it and say destination, because that's the destination, and we know then that we want this to not equal 1. So let's try and we could set a breakpoint. Well, we could set a breakpoint here, or we could set a breakpoint here where this is actually declared. So you can see here 014D9. let's go to GDB now that we can run this with PwnDbg. Now that we can run it inside a debugger, we'll do patched. Because Py is enabled, we need to run the program first. So we'll break at the main function, and then we'll run the program. And now we can say we want to break from whatever offset of the Py base, which in our case we're going to do 14D9, 0x14D9, and then continue. And if we continue this, now we're seeing that this is being set to 1. So let's take a copy of this. Let's hit next to go to the next instruction, and then let's print out RBP minus 0x8c, and you can see where it's pointing to. Let's try and print that out. Okay, it's a pointer, so we want to dereference it, or we want to access the pointer, and that's showing us a 1, so that was the 1 that was assigned. So now all we need to do is say set, and we want to set that to equal 2. Let's try and print that again. Yep, now it equals 2. So whenever it asks us now, let's hit continue. Whenever it asks us what's the destination, let's say 2, and then we just get the program's exited. But let's say we want to break at decrypt. Where's decrypt? Okay, say we want to break at decrypt. Let's do this all again. Run. It stopped at the main function, which we could actually delete that breakpoint now if we wanted. And we're going to set this again, the same thing, we're going to set it to 2. Let's print it out again to make sure it looks okay. It does. Let's hit continue. It's going to ask us now for a 2. Well, it's going to ask for something, we're going to enter in a 2, and now it's hit the breakpoint. So this is actually the decrypt function. You can see we have our data, we have our key, we have that 2 that was sent across. Don't know if that's an issue, I don't think it is. Now, if we hit continue here again, we're probably going to run into another issue where it's going to decrypt, but it's not actually going to print anything. So what we want to do is have a look at this string compare, which is where it's actually doing the comparison. So you can see here it's doing string compare with the desc node, and if it matches, it's going to say node activated. It wasn't saying node activated for us, so we want to try and see what this string compare is doing. So I'm going to take a copy of this. Let's say again break RVA 0x. We'll paste that in. Let's hit continue. We've hit that breakpoint, and the breakpoint is now telling us that it's comparing HackTheBox, do this or do that, which looks like our flag. The next challenge is called Knock Knock. It's the final challenge, and the description says, we found a backdoor on one of our servers and suspect it's being actively exploited. We believe the program was compiled in Python 3.8. Can you test it out? So there is a server for us to connect to this time, but we've got a local copy to check out first of all. So take a look at this. It's called backdoor, and we'll make it executable. Let's try and run it and see what happens. And we get this error saying error loading Python lib, and it's trying to load this lib from the temp directory. Let's try and run strings-n10. See if we can get an idea what's going on with the program. You can see these pyz files. I didn't actually see the challenge description whenever I was going through this, so I opened this up. Let me go over to Ghidra first of all. I opened this up in Ghidra, and if we go into the functions, there's no main function because it's been stripped, but if we go into the entry, we can see here this is where it starts off, and we can go and have a look through the code. So this reminded me a little bit of another HackTheBox challenge called Hiss, which I'll try and put a link up to. I did a walkthrough on that a while ago, and the start's the same, but it ends up quite different in the end. But in that, I kind of showed that we could start off by having a look for the strings in here and have a look for that Python error. Let's search Python. So this was the error that we just saw there. So we can select that, and then we'll see it here, and we'll see the references. So we can select that and go and see where is this in the code, and we can go and kind of trace our way back through the code. But if we do that, we'll see that there's a lot of functions in here, and the challenge description told us that it was to do with a Python 8. If we didn't have that description, one of the things which helped me identify this previously was to search for this string, so the MEI pass 2. If you go and search for that, I think one of the first links, let's try and good old trusted Stack Overflow will tell us, somebody's asking what does it mean, and we're being told that it comes from the PyInstaller's ancestor, Macmillan Enterprise Installer. So we know that it's to do with the PyInstaller. So because we know it's a Python binary, there are a couple of tools we can use. I think one is called PyInstExtractor. Just try and get the Git up here, but there is a couple of different ones. Yeah, we can use this one. We can also use PyDecipher, which I already have installed, so you can run pip install PyDecipher if you don't have this already installed, and then we can just try and run something like PyDecipher -d-v, so I think just decode and verbose, pass in the backdoor, and it'll go through. You see we actually get some errors in this case, and we get no artifact types found and produce no output. So it didn't actually work for me, but we can try and just use 7z and extract this. So 7z-x and then pass in backdoor, and that produces this null, which as the name suggests doesn't have anything in it, but we have this PyData which does have some stuff in it. So we could go through and have a look at for some strings and stuff in there, or we can just go ahead and try and decompile this. So let's try actually again there. Let's try it and do PyDecipher. Oh, I spelled that wrong. PyDecipher, and we'll pass in the PyData this time. Okay, yeah, so that's starting to unpack. You can use that. You can use Uncompyle6 as well. Will often Uncompyle6 will also decompile some Python files, although I do quite often have problems with it nowadays with the latest Python version. If you're ever having a lot of problems due to Python versions or compiler versions and stuff, try to go to decompiler or decompile.com or decompiler.com. Decompiler. And you can, as you can see here, you can throw in an exe or a DLL or a jar or a PYC file, which we'd be dealing with. In our case, we don't actually need to do that, because in running the PyDecipher there, if you go and have a look in this folder now, we've actually got all the files we need. And if we only had these PYC files, like source.pyc, we would need to take that to the decompiler. In fact, let me do that. Let's go to just test it out. We don't need to do it in this case, because you can actually see we've got source.py, so we have the code. We don't just have the bytecode. But if we didn't, we could decompile it here, and that'll give us access to this code. I'm just going to go and open it up in Codium instead. So source.py. And this is essentially the original code then that was compiled, the original Python code. In some cases you won't be able to get access to this, and if you have a look at my HIS walkthrough, it was different in the sense that I wasn't able to get back to the original Python code, so we just had to use the Python bytecode to try and reverse engineer the program. But in our case, we've now got the Python code. We can see that it launches a server, it waits for a connection from us, and it's going to receive 32 bytes. You can see here it's checking that the data that it receives is top secret after it's been MD5. So we could go and say echo -n, I think, so it doesn't produce a new line. And then let's do top secret. Should have copied and pasted that, but oh well. And then we can just send that to sorry, not base64. What we're doing, MD5 sum. MD5 sum, and this will give us the value. So that's what it's going to take from us to begin with. If we don't put that in, it's going to say invalid. And we then it asks for a command. It asks for the size, then it asks for a command, and if the command doesn't start with command, it's going to close. If it does start with command, it's going to replace command with nothing, and then it's going to execute whatever the command was, and it's going to return the output to us basically. So let's go ahead and just try it out on the remote server. Let's go and launch the Docker instance. take a copy of that address, and we'll go here, we'll say, oh, I should have kept that up, let me run that again. So we'll connect to the netcat first of all. Let's just see if we try and enter something in there, it just closes down. But if we try and enter in this MD5, it allows us to continue. And actually, I got a bit stuck here because I didn't notice the length check. So I did command and then ls, and you see it actually prints out the files in the directory. But if we try that again and do command cat flag.txt, it doesn't work, and I tried doing a few different tricks to get that to work. I thought it was something to do with the space, but actually it's to do with the length. So let's create a PwnTools script to solve this, and I'm going to say from pwn import all. We can set the log level if we want to print out what's going back and forward. Can sometimes be handy if you're not sending and receiving lines properly or something. And we want to set up our remote server. So IO input output is equal to remote, and then we want to put in our IP and our port number. So grab a copy of that. And our command is going to be cat flag.txt, so let's get that set up. Command is equal to command cat flag.txt, and then we're going to send that. Just make sure, no, we want to send our MD5 first of all, don't we? So I think we can just use MD5 sum in here. Let's try it. MD5 sum, and where's the password? MD5 sum, pass this in, I guess in bytes. I'm not sure how that's going to work, we'll see. And then io.send, and we want to send the length of the command, so we'll send this here as len command, and then we'll actually send the command. Hopefully that's alright. We can just go IO. We could set this to receive the output, but I'll just set it to interactive just in case there's any problems. We want to see what's going backwards and forwards. And let's try and run it. Python solve catflag.txt. It didn't work. Okay. I don't know. Maybe this shouldn't be in bytes. Let's try that again. Try that again. No. Okay. Alright. Let's just do the MD5 version then. So we'll just take the MD5 that we did first, which is right here. And unless I've made a mistake somewhere else, hopefully this will work. Oops. Run that again, and this time we get back our flag. So you can see then it sent off the MD5, it sent off the length, which was set to 20, which is the length of this full command. And then it sent the command catflag.txt. The server has replaced the command with nothing, so it's run catflag.txt, and then it's checked the output, which has sent it back to us, and that's from the sub process. So that'll wrap it up for the reverse engineering challenges. I hope you've enjoyed this video. If you have any questions or comments, or you solved anything differently and want to let me know some cool tricks, then leave a comment below. Thanks.